Good morning. My name is Nick Harper, and I will be presenting on the security aspects of HTTP3 and QUIC. I've been working on implementing QUIC at Google for the past few years, and I also participate in standardizing the protocol at the IETF. QUIC is a new general-purpose transport protocol. It is always encrypted and provides multiple streams of application data in the same connection, with packet loss on one stream not affecting other streams. HTTP3 is an application protocol built on QUIC that provides HTTP semantics. Its feature set is practically identical to that of HTTP2. The purpose of QUIC and HTTP3 is to improve performance compared to HTTP2. Over the course of this talk, I will show how the protocol stack for HTTP3 differs from HTTP2 and examine in detail many of the features that are moved into the QUIC protocol. I will also explore security-related mechanisms used in QUIC throughout the lifetime of a QUIC connection. Let's start by looking at how the HTTP2 protocol stack differs from HTTP3. At the bottom of both protocol stacks, we have IP, which transmits messages between two addresses on the internet. The next layer up in the HTTP2 protocol stack is TCP. TCP provides an in-order, reliable byte stream and allows the operating system to dispatch incoming connections to different processes based on port numbers. TLS runs on top of an in-order, reliable byte stream, such as the one provided by TCP, and it provides that same abstraction to the level above it, but TLS adds confidentiality and integrity to its messages. HTTP2 sits on top of this whole stack, and it provides a way to multiplex streams on a single connection. In HTTP3, all of the functionality that I just described is moved into the QUIC protocol. Let's start by examining the transport handshake in QUIC and how that compares to a TCP handshake. In this packet trace, we have a client on the left which initiates a QUIC connection, and a server on the right. In a TCP three-way handshake, when the client receives a SYN ACK from the server, it can verify that it had to be in response to its SYN. Likewise, when the server receives the first ACK from the client, it can verify that it was in response to the Likewise, when the server receives the first ACK from the client, it can verify that it was in response to the server's SYN ACK, and since the SYN ACK was sent to the source IP address in the SYN packet, the client is able to send and receive packets at that address. In the QUIC handshake, we have similar confirmation that the client is able to send and receive packets at its source IP address. The client can verify that the server's TLS handshake messages are in response to the client's TLS client hello, and the server can verify that the client's TLS finished message is in response to the same TLS connection. Just like how the TCP SYN ACK message was sent to the client's source IP address, in QUIC the server's TLS handshake messages were sent to the client's IP address, and getting the TLS finished message proves that the client controls that IP address. In TCP, the server's SYN ACK message is sent without knowing if the sender of the SYN controls the source IP address from the SYN packet. If the client spoofs the source IP address of its SYN packet, it can get the server to send a SYN ACK to another endpoint. Before the client's IP address is validated, a hypothetical protocol running on top of IP might allow a client to send a small packet with a spoofed source IP address to a server that would result in a large packet being sent by the server to the victim in an attempt to DOS the victim. This attack is only useful if the server's packet is noticeably larger than the client's packet, since otherwise the client could send traffic directly to the victim. In TCP, this attack isn't a concern because the SYN and SYN ACK packets are both small and roughly the same size. In QUIC, both the client's initial packet and the server's first flight of packets are much larger than a TCP SYN or SYN ACK packet. To avoid this amplification attack, QUIC imposes a limit on how much data the server can send before the client's address has been validated. The server is limited to sending 3 times the amount of data that was in the client's packet. The client can expand its initial packet by adding padding to allow the server to have a larger response. However, if the server needs to send more data in the handshake than fits under the amplification attack limit, the server can explicitly request address validation at the cost of 1 round trip. The server does this by sending a retry packet, which contains only an address validation token. The client puts this token in the header of its next initial packet, and echoing it back to the server proves the client controls its source IP address. At this point, since the address has been validated, there are no limits to the size of the server's TLS handshake messages. This retry token can also be used to mitigate QUIC's equivalent of a TCP SYN flood. Upon receipt of a TLS client hello, the server has to maintain state for the QUIC connection. If an attacker floods the server with client initial packets, the server has to store state for each of these connections. At the cost of 1 round trip, the server can defer the cost of creating this state until after address validation. It does this by sending a retry packet to the client. Deferring the cost of creating state is done by encrypting all of the state, the client's connection ID, its source IP address and port, and any other state the server might need in the retry token. That way, no state apart from the encryption key for the retry token is needed on the server. In the transport handshake, in addition to confirming that the client controls its source IP address, additional transport connection properties are established. This includes flow control limits and other properties. In TCP, these are advertised in the TCP header. In QUIC, these limits and other connection properties are advertised in the transport parameters TLS extension. Unlike TCP, where a network intermediary can alter the TCP header, the transport parameters are authenticated by the TLS handshake and encrypted in the server-to-client direction. In either direction, an attacker cannot tamper with the contents of the transport parameters without causing the TLS handshake, and thus the QUIC connection, to fail. Now let's look in a little more detail how these packets appear on the wire. QUIC packets, regardless of what version of QUIC, have either a long header or a short header. Long header packets are used during connection establishment, and the short header packets are used once the handshake is complete. The first bit in the packet header indicates whether the header form, which header form is in use. A 1 indicates a long header, and a 0 indicates a short header. Long headers include the connection IDs of both the sender and the receiver, while short headers only include the receiver's connection ID. For the rest of this talk, I will be focusing on QUIC version 1. The packet formats for those versions have a little more details than described on this slide. This slide shows what is in a QUIC packet header for any version of QUIC. I've mentioned on this slide and in previous slides QUIC connection IDs. So let's look at how those work in a little more detail. QUIC uses connection IDs to identify a connection instead of using the 5-tuple of IP protocol, source and destination IP addresses, and UDP source and destination ports. Connection IDs are variable length, ranging from 0 to 20 bytes. Each endpoint chooses its own connection IDs and advertises those to its peer. An endpoint can have multiple connection IDs for a single connection. Multiple connection IDs are provided for a single connection so that each network path used for a connection can use a different connection ID. An endpoint needs to be able to route a packet based on its connection ID to the correct QUIC connection, and the connection ID should appear random to an external observer. Load balancers can use connection IDs to route packets to specific servers, assuming that there is cooperation and coordination between the server fleet and the load balancer sitting in front of that fleet. Cooperation is required because servers issue connection IDs, and load balancers need to process enough of that connection ID to route it back to the server. There is a draft in progress that describes multiple ways that load balancers and servers can cooperate. The suggested way, at a high level, is that the servers and the load balancer share a key and encrypt a connection ID. The plaintext of that would contain a server ID and a section to identify that connection on the server. And then the encrypted connection ID is put on the wire. If connection IDs do not appear random to an external observer, there are two possible attacks. The first attack is a privacy leakage. If an observer can tell whether two connection IDs belong to the same connection, it can look at traffic flows on different 5 tuples and correlate connections as being the same connection. The second attack involves load balancers. If an attacker can generate many connection IDs that the load balancer will map to the same server, the attacker can bypass the load balancer to mount a denial of service attack on the specific server behind the load balancer. Now that we've looked at the transport handshake and connection IDs, let's look at how the crypto handshake works in QUIC. So to start off, the crypto handshake in QUIC is the TLS 1.3 handshake. When run over TCP, TLS provides a record layer which handles multiplexing handshake and application data on the same connection. This record layer also handles encrypting the data sent on the connection. TLS assumes that it is run on an in-order reliable byte stream. In QUIC, the TLS record layer isn't used. Instead, QUIC has its own record layer to handle encrypting packets. The TLS handshake still depends on its handshake messages being delivered in order and reliably. The use of TLS 1.3 in QUIC, its handshake, relies on QUIC transport features handling reordering and retransmission of packets containing the crypto handshake. So on this slide, we see that the TLS handshake messages are in QUIC crypto frames, and if a packet gets lost, QUIC will retransmit that crypto frame in a future packet. The crypto handshake, in addition to establishing crypto parameters for the connection and keys to use, also carries the transport parameters for the connection, as I mentioned earlier. The crypto handshake also contains the ALPN for the connection, the application layer protocol negotiation tag. So this would be, for example, HTTP3. So TLS provides keys to QUIC to use for record layer encryption, but QUIC handles that record layer encryption itself. The encryption keys used for a QUIC packet are determined by the type of packet. Handshake packets in QUIC use handshake keys from TLS. ZeroRTT QUIC packets use ZeroRTT keys from TLS. And short header packets in QUIC use application data keys from TLS. The application data keys used to protect short header packets provide forward secrecy. The TLS 1.3 key schedule derives traffic secrets for each encryption level, which maps to a QUIC packet type. A single traffic secret at each encryption level is used to derive multiple secrets, including encryption keys and IVs for both sending and receiving by each endpoint. Let's look in a little more detail how QUIC record protection or record layer encryption works for QUIC v1. In QUIC, every packet is encrypted using an AEAD mode of encryption. And every packet in QUIC has a packet header, which contains a packet number and a payload. Let's look at how these elements of a QUIC packet map to the inputs of the AEAD encryption function. The AEAD encryption function takes 4 inputs: K, the key, N, a nonce, P, the plaintext, and A, associated data, and outputs a ciphertext C. When encrypting a packet at some encryption level, we have a key and an IV that are derived for that encryption level. We use that key as the key K for the AED operation. The nonce is derived from the IV and the packet number for the packet being encrypted. The plaintext is the payload of the packet, and the associated data is the packet header. The ciphertext output C is then transmitted on the wire in place of the plaintext P. This provides confidentiality and integrity for the packet payload. It also provides integrity for the entire packet, since the header is used as the associated data. Because of this integrity guarantee, QUIC packets cannot have their headers modified by network intermediaries, unlike TCP packets, where headers are often processed and modified by intermediaries. In the example on this slide, we see the start of a packet on the first line. The first byte, colored in red, identifies whether the packet is a long or short header, and a few of the bits in there are used for additional purposes. Next, this packet header has a connection ID, highlighted in yellow. The length of the connection ID is known by the receiver ahead of time. Finally, the packet header contains a packet number. In this case, the packet number is 1 byte long. Some of the lower bits in the first byte of the packet header indicate the length of the packet number. And then finally, we have the plaintext for the packet. The second line shows how the plaintext of the packet payload is replaced by the ciphertext that was output from the AED function. After this encryption has been done, there's an additional step done to encrypt the packet number in the header and some of the bits in the first byte of the packet header. During the key derivation step, where we got the key and IV to use, there was a third secret that was derived, which is the header protection key. This header protection key is used to perform a single encryption operation. It takes as input 16 bytes that are sampled from the encrypted ciphertext of the packet and outputs a mask. This mask is shown on the third line of this example. And the mask is XORed with certain bits of the packet header to result in the encrypted packet header. We can see in this example that the last 5 bits of the first byte of the mask are XORed with the first byte of the packet header. This obscures the length of the packet number in the header. And then the rest of the mask is used to XOR with the packet number to encrypt the packet number. The final line on this slide shows what the packet that actually gets sent on the wire looks like after the encryption and header protection are applied. To decrypt a QUIC packet, these operations are applied in reverse. First, the header protection mask is computed and then XORed with the same bit pattern to decrypt the header. Then, once the packet number is decrypted, the receiver can know the nonce to use and can run the AED open function to get the plaintext. Or the AED decrypt operation could fail. If an endpoint receives a packet that fails to decrypt, the packet is discarded. This prevents an attacker from being able to inject packets into a QUIC connection. When short header packets are used, the only parts of the packet header that are in the clear are the 3 bits at the beginning of the packet and the connection ID. Everything else is encrypted. This example has a short packet header, so the 3 bits in the first byte of the packet header are in the clear. The connection ID is in the clear, but everything else in the packet is encrypted. When using QUIC's record layer encryption, there are a few considerations regarding multiple encryption levels. The first is that initial packets are protected with obfuscation keys. These are derived from the connection ID and the QUIC version, which means that anyone can derive these keys. Once initial encryption keys aren't needed, these keys should be discarded to prevent an attacker from injecting packets at the initial encryption level. Also, each type of frame in QUIC can only be sent and received at certain encryption levels. For example, most frames that are sent in ZeroRTT packets can't be sent in handshake packets. In particular, if a client mistakenly sends a stream frame in a handshake packet, there could be a loss of confidentiality if the client is not able to authenticate the server. So, endpoints should make sure that they only send frames at the correct encryption levels. In addition to ensuring that frames are written at the correct encryption levels, implementations should also check that incoming frames it reads were sent at the correct encryption levels. For example, a server should not accept an initial packet that contains a stream frame. Now that we understand how the transport and crypto handshakes work in QUIC, and how QUIC encrypts data, let's take a look at some of the other details of the QUIC transport. The payload of a QUIC packet is made up of a series of frames. A QUIC frame starts with an indicator of what type of frame it is, but otherwise, frames are not self-describing. We've already seen examples of two types of frames on previous slides, crypto frames and ACK frames. And I've also mentioned stream frames. So, application data in QUIC is carried in stream frames. A stream is a lightweight abstraction for a reliable in-order byte stream, and it is identified by a stream ID, which is a 62-bit integer that is unique across all streams on that particular connection. One of the responsibilities of a transport protocol like QUIC is managing flow control. QUIC has an overall flow control limit for a connection. It also has flow control per stream and flow control for the number of streams that can be open at a time. These limits are initially set in transport parameters. During the connection, they are updated via max data, max stream data, and max streams frames. Unlike TCP, where flow control is in the clear in the TCP header, these frames are all part of the packet payload, and thus they are encrypted and not visible on the network. Receipt of QUIC packets is acknowledged in ACK frames, which again is information protected in the packet payload instead of in clear text like in TCP. When data is lost and retransmitted in QUIC, it is retransmitted in new packets. Unlike TCP, packet numbers or sequence numbers are not reused. When a QUIC connection starts using a new network path, the new network path must be validated before use. An endpoint does this by sending a path challenge frame and then waiting for a path response frame. I'll now talk about some implementation considerations that could have security impacts. The first one regards flow control. If an endpoint advertises flow control limits but never enforces them from the peer, then the peer could flood the endpoint with data, leading to resource exhaustion. If an endpoint does not do path validation before using a new path, then its peer could cause that endpoint to flood a victim with traffic. For HTTP2, there is a CVE 2019-9517, which was a bug in implementations and deployments, where a malicious endpoint could advertise a large flow control window at the HTTP2 layer, but at the TCP layer, it would close the flow control window. This would result in the victim thinking at the HTTP2 layer it can send a large amount of data, but at the TCP layer it can't, and then a large amount of data would be buffered in the HTTP2 layer. In HTTP3, both the per stream and per connection flow control happens in the same context in the QUIC layer. So a QUIC implementation can simply apply the minimum of the two flow control limits for the per connection flow control limit and the per stream flow control limit, and thus avoid the extra data buffering where it thinks it can send more data than it actually can. When this CVE was reported, there were multiple other CVEs reported affecting HTTP2. The key takeaway from all of these CVEs is that an endpoint's peer shouldn't be able to cause the endpoint to use unbounded memory. Many of the mitigations for those other issues apply to QUIC as well. So far, when examining how a QUIC connection gets established, we've looked at fresh connections. Now let's look at how QUIC handles resuming connections, including one of QUIC's biggest features, which is how it allows a client to establish a connection with zero round-trip time, or ZeroRTT. On a fresh connection, a QUIC server has the option of waiting an additional round trip to validate the client's source IP address before continuing the handshake. It does this by sending an address validation token in a retry packet. A server can also send an address validation token to a client in a new token frame. This token can be used by the client on a future connection to prove that it controls its source IP address. You can think of this as being very similar to a TCP fast open cookie, which allows ZeroRTT TCP connection establishment. When a server generates address validation tokens, whether they are in a new token frame or in a retry packet, the server must ensure that an attacker cannot forge these tokens. If an attacker can forge an address validation token, the server is vulnerable to participating in an amplification attack. An endpoint could receive an unbounded number of new token frames from its peer. It should limit how many tokens it stores, and if it receives more tokens than it has room for, it should discard old ones to avoid storing an unbounded number of tokens. The other aspect of being able to establish a ZeroRTT QUIC connection involves the TLS handshake. TLS 1.3 has a ZeroRTT resumption feature, which QUIC also uses. This works by having the server send a new session ticket to the client after the TLS handshake completes, and the client uses that new session ticket to perform ZeroRTT resumption on a future connection. Effectively, the way this works is that both parties remember a shared secret from one connection and use that secret to derive keys that the client can use to send ZeroRTT data on a new connection. Let's look at the start of a ZeroRTT handshake. This diagram shows what the packet flow for a ZeroRTT connection looks like. The client includes a retry token T in its initial packet for the server to use for address validation. The client received this token on a previous connection and is assuming that it has the same source IP address from that previous connection. If the server notices that the client is on a different source IP address, the server can discard that token and either perform address validation or assume that the address is not validated and handle this like it would in a 1RTT connection with amplification attack limits. In this initial packet, the client sends a TLS client hello to resume a TLS connection. It includes the early data TLS extension, which indicates that the client will be sending ZeroRTT data. The client can then send ZeroRTT QUIC packets containing stream frames with application data, and these packets are encrypted using the ZeroRTT keys derived from TLS. These keys are known only to the client and the server. There are two caveats to be aware of when using ZeroRTT data. The first is that data sent under ZeroRTT keys is not forward secret. The endpoints must wait until the handshake is complete to be able to send data with forward secrecy. A separate issue is that ZeroRTT data can be replayed by an attacker as if it were the beginning of a new connection. For example, a ZeroRTT packet from a client might contain an HTTP request. An attacker can observe these initial packets and then send them to the server a second time. The server at this point has no way of knowing, did those packets come from a live client or did those come from an attacker who has replayed them? Whatever processing that the server does with the data in the ZeroRTT packet, it needs to be aware that it might receive it multiple times. For example, in HTTP, it is recommended that only safe HTTP methods like GET, HEAD, or options are used in ZeroRTT data. Ultimately, it is up to the protocol and the server to decide what data in ZeroRTT is acceptable and what data it will wait until the handshake is confirmed to process. The caveats here that I've described for using ZeroRTT data in QUIC are the same ones for using ZeroRTT data in TLS 1.3 over TCP. So we have now looked at how QUIC connections get established, how they can be resumed, and some of what happens when a QUIC connection is running. Now let's talk about how a connection is terminated and how an attacker might use those mechanisms to close a connection it does not control. The easiest way to close a QUIC connection is by sending a connection close frame to terminate the connection immediately. Remember that since QUIC frames are part of the protected payload, an on-path attacker can't inject a connection close on a connection when the handshake has been confirmed. An attacker can only inject connection close frames if the endpoint is still receiving initial packets. A connection can also be closed by idle timeout. If an endpoint receives no new packets after a determined amount of time, it silently closes the connection and discards its connection state. An on-path network attacker could drop all packets for a connection. There is nothing the transport protocol can do to mitigate this type of connection close besides moving the connection to a different path. The last way a connection can be closed is via stateless reset. If an endpoint loses connection state, for example, because the endpoint just restarted, it may still be receiving packets for a connection it previously established. Since the endpoint no longer has the encryption keys for that connection, it wants some way to signal to its peer that the connection is closed. This is to save time waiting for the connection to time out and to save bandwidth and processing while the peer is flooding this endpoint with packets. The endpoint can signal this connection close with a stateless reset packet. Earlier in the connection, when the endpoint provided its peer with its connection ID, the endpoint also provided a stateless reset token. If the peer sees that stateless reset token in the future, it knows that the endpoint is closing the connection. An endpoint constructs this stateless reset token by using some global, not per connection state so that it can deterministically derive the token from the connection ID of the incoming packet. For example, this can be done by using a secret key on the server that persists through this restart, and then computing an HMAC or an HKDF of the connection ID of the incoming packet. It is important that whatever mechanism is used here keeps this key secret, because if an attacker gets a hold of that secret, it can compute stateless reset tokens for any connection and inject those and close connections it's not a part of. This concludes our exploration of the HTTP/3 protocol stack and its security features. In summary, the HTTP/3 protocol stack has the same security features and properties as the HTTP/2 protocol stack. Most of the functionality has been moved into the QUIC protocol. HTTP/3's use of QUIC provides improved performance compared to HTTP/2. QUIC's use of encryption and authentication prevents the network from modifying transport connection properties. This encryption and authentication also improves privacy compared to TCP by making the connection ID the only unencrypted part of the packet. This also benefits future protocol development. Thank you for watching my talk, and I will take any questions now.